We'll start off with the announcements. I guess this is the last time we'll meet in the second week. I only do this for the first 2 weeks of the course, and then after that, I expect you to behave responsibly as college students. You have the email that's due today, the syllabus quiz on D2L that is due tomorrow. Extra credit practice problems. There were some that were due last night, and the second half due tomorrow night. The Chapter 2 Mastering Chemistry homework quiz is due on Monday. Any questions on the syllabus? Yes, sir.
You can't retake the syllabus once we do it once, right?
You do it one time, yes. Yep, because you'll have all the answers in front of you with the syllabus. You take it. So, anybody else? Okay, last week you had required safety training. That was required to participate in lab activities. Yeah, and so I think the other half of your meeting at 1:30 today with Professor Creel. You need to make sure that your pre-lab quiz is due before and completed before you go participate in lab each week. If you're still having trouble activating your access code to Mastering Chemistry, don't forget there's a 14-day free temporary access that's available. If you are unsure of how to do that, do see me. I can't on the instructor side show you, but if you come to my office, I can easily demonstrate that for you. You do have the Socrates student app that you should be logging into every day when you come in here. There will be at least one question waiting for you. You'll go into the room Chem Lancer and sign in with your chemical symbol in place of your name. And then we have the element quiz that is due on Monday, February 4th. We will provide more details about that next Tuesday when you come to class. But just as a very, very brief, quick heads up, which elements should you be studying? The gray ones. And we need to know two things about the elements. We need to know the name with. Correct.
Case.
The name with. Correct.
Spelling and case.
Spelling. And then your chemical symbol with the proper case or capitalization. So those are the two things you need to know for the periodic table. And we'll provide more details next Tuesday. There will, after class on Tuesday at 1:30, Tuesday, there will be opening up on D2L a quiz on there that you can then take your element quiz on. That'll open up after class, immediately after class on Tuesday. Last thing, that's it. So any questions before we go on? Okay, the question waiting for you on the Socrates app today was, we have a gas tank on a medium-sized car holding 15 gallons of gasoline. This quantity is the same as how many liters? Give the answer with the correct number of significant figures. The correct answer here is 57 liters, not 5. Where the heck are you getting 5 significant figures? It's 2 significant figures, because if we look at this particular problem, 15 has how many significant figures? 2. Exactly, there are 2. So if you were to put this into a calculation, you'd start with your 15 gallons. Most of you probably went to your conversion sheet, and in looking at your conversion sheet, you would have pulled out this conversion right here that says 1 gallon is 3.785 liters. If you would use that, then where does the gallon go? On the bottom, which means that the 3.785 liters goes on top. What happens to gallons? Cancel out, actually get reduced down to 1 over 1. If you multiply this through, you're probably going to get 56 point something. That's going to round off to 57, because again, this number here has 2 sig figs. This conversion has how many significant figures? 4. And you're told that right here in the conversion table that this has 4 significant figures. So the fewest of 2 and 4 is 2. Which means the answer should have 2 significant figures. What else is this answer missing? Units. The units would be liters. Any questions? Okay, Next up, we have 65 miles per hour, and we'd like to convert 65 miles per hour to SI units. So if we want to convert 65 miles per hour to SI units, we need to first of all realize what are SI units, which of course, again, we talked about SI units in here last Tuesday. Looks like the units are going to be a length per time unit. So what is the SI unit of length? It's a meter. What is the SI unit of time? I hear seconds and minutes. What is it? It's seconds. So if we're going to express this in SI units, we are going to express it in units of meters per second. Now, I am telling you what it is now. If you saw this on exam, you would need to know that it was meters per second. Because again, you would see this as a length per unit of time. That means you need to express your answer in a length per unit of time. And again, in SI units, that would be meters per second. So now when we calculate this, if you were to write it as 65 miles per hour like this, I can almost guarantee you that at least half of you in here are going to calculate the wrong answer. When you do these conversions, you want to very clearly show what belongs in the numerator and what belongs in the denominator. Not both of these units belong up above. Which one belongs on the top in the numerator? And in the denominator would be?
1 hour.
1 hour, or simply hours. We'd say 65 miles per hour, or 65 miles per 1 hour. And so we're going to go ahead and convert this over to meters per second. And I'm going to give you a few minutes to do so. You're probably going to require at least 3, probably 4 different conversions to do this. So go ahead and do this conversion. If you don't know where to start on this, the best place is to ask a neighbor. Please don't use the next few minutes to stare into space, having no idea what you should be doing. If you don't know where to start, turn to someone that looks like they know where they're starting from. Now understand, you will not be converting both the numerator and denominator at the same time. You can work on the denominator first or the numerator first, whichever one you want to start working on. Personally, I think it's easier to start working with the numerator first. So start converting miles to something. Once you get your numerator properly converted, then start working on the denominator. Now, the way you start may not be the way your neighbor starts. That's okay. I was growing up, there was a saying that says there's a million ways to skin a dead cat. I'm not sure there's a million ways to solve this one, but there's quite a few. Anybody that needs some new conversion sheets? Exactly, never can have too many. While you're working on that, I'm going to pass out handouts a bit today. All right, let's talk about how we might go about solving this. I understand some of you might not be done, and that's okay. Those that are done can look at this, and those that aren't might need some help anyhow. So let's start first of all by converting the numerator. What can we convert miles to? Kilometers would be 1. Anybody start a different way? Which way did you go? To feet. All right, let's do kilometers since that was the first one mentioned up here. And let's go feet down here. Oh yeah, now which way do we put this? Do we put the kilometers up above or the kilometers down below?
Up above.
Up above. So let's do a conversion of miles to kilometers. That's going to come from our conversion sheet. This would be an English to metric conversion. We see that 1 mile is 1.609 kilometers. So where would the 1.609 go? On the top, okay? And then on the bottom would put in 1 mile. Now suppose you're starting with feet. Does the feet go up above like I've shown here, or do the feet go down below? Feet would go up above. And on the bottom would put in miles. This one here, we have an English to English conversion. This very handy number of 5,280 feet for every 1 mile. So we come back here, put in the 5,280 feet up above for every 1 mile. Those units cancel. Now if we stopped our calculations at this point, I don't know where my, here it is. If we stopped the calculations at this point, what would the units be?
Kilometers per hour.
Kilometers per hour, and here it would be?
Feet per hour.
Feet per hour. Okay, now of course we're not where we want to be yet. So let's take the bottom one here. Let's go from feet to meters. How do we go from feet to meters? Alright, so we come back here. Looks like we have this conversion that shows 1 meter is 3.281 feet. So again, 1 meter is 3.281 feet. Where does 3.281 feet go? The bottom. And on the top would put in the 1 meter. These cancel. Now if we did the conversion up here, which units are going to go on the bottom?
Kilometers.
Kilometers. And on the top would put in? Meters. So now this one, if you went back to your conversion sheet, you're not going to find it because this is one of those things where you need to memorize those prefixes. So what is the conversion in meters and kilometers?
1,000 meters to 1 kilometer.
1,000 meters to 1 kilometer. Why isn't it 1,000 kilometers to 1 meter? Kilometer is bigger. Because a kilometer is bigger, it's going to have the smaller number. So there's 1,000 meters for every 1 kilometer or 1 kilometer. These cancel out. Now if we were to stop at this point, we should wind up with units of
Meters per hour.
meters per hour. So now let's work on the denominator. For every 1 hour, we have 60 minutes. So where does the 1 hour go?
On the top.
On the top. So on the bottom we'd put in 60 minutes. And of course that means that hours are going to cancel. And then for the next conversion we'd say for every 1 minute we have 60 seconds. And again, minutes are going to cancel out. Now some people like to go directly from hours to seconds. That's okay. If you did hours to seconds, on the top we could put in, on this one, 1 hour. And every 1 hour has how many seconds? 3,600. Now, I had quite a few people that did this one this morning, and that's fine. One mistake you want to be sure to avoid, and it's a very common mistake I see very often, 1 hour, 60 seconds. So if you're going to go with the direct conversion of hours to seconds, make sure that you do that in advance. Now, if you go through this, your hours are going to cancel. If you run through the calculation, what number do you wind up obtaining in the end for an answer? Should be 29. Should be 29. You should wind up with 29 for each one of these. Now, if you didn't get 29 but had it set up right, what you need to remember is that when you go through these calculations, when you're multiplying fractions, you're always multiplying together all the values that appear in the numerator, and you're dividing by each number that appears in the denominator. Because of course here you're multiplying by 1/60th, here you're multiplying by 1/60th. That's the same as dividing by 60 and dividing by 60 again. So a very common mistake is I'll see people multiply these together. They'll divide by 60 and then they'll multiply by 60. But you don't multiply by 60, you have to divide by 60, because that'd be the same as multiplying by a fraction of 1/60th. But set up the bottom one, I do pretty much the same thing. If I do the bottom sequence, it would look like this. I would take 65 and multiply that by 5,280. I would divide it by 3.281, and I would divide it again by 3,600. And upon doing so, you see I wind up with 29.05, etc. This answer, though, should have 2 significant figures. And what is it that gives us the 2? What do we look at to guide us to the 2 significant figures on this one?
The measurement that's got the fewest number of significant figures.
The measurement of the fewest sig figs. This one here that we're given has 2 significant figures. How many significant figures in this one? It's an infinite number. It's infinite because this is an exact conversion. Remember, exact conversions have an infinite number of sig figs. So this has 2. This is infinite. This has how many? 4. And this one here has? Not
Infinite.
4.
Infinite.
Doesn't have 5.
Infinite.
It would be an infinite number because, again, when we have time, it's exactly 60 seconds in 1 minute, exactly 60 minutes in 1 hour. So it's not 59.99999 seconds, it's exactly 60 seconds in 1 hour. When it's the exact conversion, it has an infinite number of significant figures. So the fewest of those in would be 2 significant figures, and that's why we rounded off to 29. Any questions on these? Go ahead. Okay, anybody else? Okay, the next question. I have lead and feathers, some of each. In fact, I have a pound of lead and a pound of feathers. And I'm making the statement that a pound of lead is heavier than a pound of feathers. Is this statement true, or is this statement false? And we'll get our answers locked in. We'll count down. 5, 4, 3, 2, 1. It is false. Now, it's false because if I have a pound of each, I'm measuring it on something like a scale. A pound is a pound is a pound. One isn't heavier than the other. They both have the same weight. So what is different between the two? Somebody said it. The volume is different, sure. And what is different about the volume? Let's say I had a pound of lead and a pound of feathers. Which one is a bigger volume? I don't know. Have you ever picked up lead before? Okay, now I don't have it here, but if I had a big metal bar and a pound of metal of any type, just pick your metal, or a pound of feathers, and you look at them, which one is going to have a bigger volume? Feathers should, sure. I mean, think of a feather pillow or something like that. It's going to be a pretty big pillow in order for you to get to 1 pound. A pound of a metal is going to be a relatively small amount. So the way they differ from each other is volume. And then, of course, because they have a different volume, turns out that they would wind up having a different density as well. And so what we're going to do here in Chapter 2, we're going to wrap it up with a look at density. And we define density as being the mass per unit of volume. Mass per unit of volume. Now when you look at these definitions, you should be able to look at a definition and write out a formula for that. Excuse me. Because the word per mathematically means to do what? Means to divide. So if we had to write out a formula, it would say the density is equal to mass divided by volume. Good. Mass divided by volume. And of course, we would put that in symbols. We would say D is equal to M over V. Here's the first of equations that you need to learn in here. D is equal to M over V. So now I have a block of wood over here. And what I'd like to do is to measure the density of this block of wood. Let's calculate its density. What sort of measurements do we need to make? What's one we need to make? We need to weigh it, or mass it, however we'd describe that. So we can go ahead and put it on the balance. Just happen to have one right over here. Surprise, surprise. So we're going to measure it, and we're going to say that the density is equal to, start again here, density is equal to, and let's go ahead and pop it onto the balance. It's reading 0, 0 here right now. So we'll go ahead and place it onto here. Looks like we have a mass of 233.69 grams. So we'll put in 233.69 grams. And of course it seems to vacillate back and forth. I'm seeing sometimes 233.70. Is that a big deal? No, because remember that there's always going to be some uncertainty in each measurement. Now what else am I going to need for this? It's volume. And how? Now I've been carrying this around for 30-some years, as long as I've been teaching. So that's why it has kind of some rounded edges I've been dropping and everything. Let's just assume it's a perfect block. If I want to find the volume of this block, what's one way I could do it? Length times width times height, sure. So we go ahead and take a ruler and measure the length, width, and height. And we'll go ahead and place it into the calculation here. So again, volume is equal to length times width times height. So I'm going to put the volume in the bottom, And because it has these rounded edges and everything, I'm not going to worry about going out to the nearest hundredth of a centimeter. So this one looks like it has a length of about 16.9 centimeters. And then we'll measure its width. Looks like we have a width of about 8.7 centimeters. And then we'll measure its height, or its thickness, whatever you want to refer to it as, and it looks like we come up with 3.6 centimeters for the thickness. So now if we want to calculate this, remember this is nothing more than multiplying fractions. We're going to take 233.69, we're going to divide it by 16.9, we'll divide it again by 8.7, and we'll divide it again by 3.6. So we'll take 233.69, divide it by 16.9, divide it again by 8.7, and divide it again by 3.6. Now part of the reason why I don't first calculate the volume is because I'm trying to avoid rounding errors. One of the very big things I see is that students will calculate an answer here, then they'll plug it in here, then they'll take that answer, plug it in over here. The more rounding you do successively, the more likely it is you're going to wind up with error in your calculation at the end. So what you ought to do then, and this is the way Mastering Chemistry does it, and I'll hear sometimes in the back of answers in the back of your book, I'll hear things like, oh, I didn't get the same answer in the back of the book. The back of the book had this is what I had. And I say, well, were you rounding off at intermediate answers and carrying it through? If the answer to that is yes, you need to go back and make sure that you don't do any rounding as the practice until your final answer, or minimal rounding. Yes?
In this case, would the weight be the same as the mass?
The weight and the mass are not the same thing. Weight is something that depends upon gravitational attraction. The mass is something that is a representation of the amount of matter that's in something. Mass is something that stays constant wherever you are in the universe. Weight is something that changes. Now that said, by rights, we should be measuring the mass on a balance. This is a scale which really should be measuring weight, because this is actually a spring-loaded type thing. But because we are here on the surface of the Earth, it practices the same bad habits that chemists do, and that is it confuses mass and weight. And that's why we talk about weighing it, when really what we're doing is massing it. Okay? But we're measuring it in units of grams, which is a unit of mass. And I gave you a long answer, which for some of you probably just went over your heads, and that's okay. It's just that, and that's because we're chemists in here, and chemists kind of get these things mixed up anyhow. So with that, if we calculate through all this, on our calculators, what do we wind up with for the answer? 0.4415. The number of significant figures in the answer should be 2. Because we have 2 sig figs here, 2 sig figs here. The unit should be?
Grams per centimeter squared, or cubed.
Centimeters cubed, exactly. Grams per cubic centimeter would be the units. Now, if you were to turn to page 40 in your text, and I don't have mine with here, but if you turn to page 40, you'll see that there's a table of, oh, you got yours there. There's a table of densities of a number of different substances. And if you look at how these are labeled here, these are shown in grams per cubic centimeter. To read through some of the same problems, in fact, that same problem on the top of page 40 calculates the density in the units of grams per milliliter. And so if I were to ask you, what is the difference of a density in grams per cubic centimeter and grams per milliliter? The answer is nothing. And why is there no difference? What did we say the other day about cubic centimeters and milliliters? They're the same thing. So while we calculate it like this, very often if we're calculating a fluid volume, we'd represent it in milliliters. But even then, it doesn't really matter, because a gram per milliliter and a gram per cubic centimeter are the same thing, because a cubic centimeter and a milliliter represent the same amount in volume. Now, one of the other things we should do here is when we calculate an answer, we should be asking ourselves, does this answer make sense? Now, at this point, you say, well, how in the world would I look at it? And I've not done a good job of doing that with you guys up to right now. How would we know if this answer makes sense? Say I go out to the river and throw this block of wood out in the river. What's going to happen to it? It's going to float. And if it floats, that means its density is less than that of water. Exactly. Well, then you must say, well, what is the density of water? Well, this is really easy. The density of water is about 1. As long as we're dealing with units of grams per milliliter. It's not 1 if we're in pounds per cubic feet, but if we're in units of grams per milliliter, the density of water is about 1. So if you calculate the density of a block of wood and you come up with a value of less than 1, you should feel pretty happy, pretty darn good about it, because a block of wood should float on the water. Now, if you want to calculate an answer of like 5,000 grams per cubic centimeter, you shouldn't feel very good about it, because actually there's nothing that's that dense here on the surface of the Earth. The most dense element, the most dense substance on the Earth is the element osmium, and this has a density of about 22 grams per milliliter. So anything more than 22 is an impossible value unless we're talking about nuclear material. And we just don't have nuclear material sitting around anywhere. We don't have nuclei sitting around anywhere in the lab or anything we'd ever come in contact with. Now, just so you know that when it comes to exam time, I always try to put questions on there which you can ask yourself, does this answer make sense? For example, if you were asked to calculate the weight of a baby and came up with a 5,000-pound baby, that answer should make no sense. Or if you have a snail traveling at the speed of light, probably shouldn't make a whole lot of sense. I'll still have some of you calculate that, I promise I will. Okay? But hopefully it would throw up some big red flags for you if you have a snail traveling at the speed of light, that probably doesn't make a whole lot of sense. Okay? So likewise with this one, if it's greater than 1 in units of grams per milliliter, it shouldn't make sense. Okay, next up, let's look at this one. I have an empty graduated cylinder. We're going to do a word problem here. And so we'll start with this. An empty graduated cylinder has a mass of, and right now I don't know what it is, we'll measure it here in just a bit. Then we're going to say that blank milliliters of water is added to the graduated cylinder. And then the question is, what is the combined mass of the cylinder and water? What is the combined mass of the cylinder and water? So let's go ahead and measure these here right now, and we're going to fill in the blanks on these. First one here, we'll go ahead and measure the mass of the cylinder, and we'll put this on, and we find out that we have 100.57 grams. So we can fill in the blank and put in the 100.57 grams. And then the next thing we're going to do is we're going to place some water into here, and we'll measure its volume. Okay. And when I measure the volume on this one right here, it looks like, is that right on there? Looks like we're maybe just a little bit above. Looks like we have about 55.3 milliliters. So again, we'll put in the 55.3 milliliters. And then what we'd like to know is, what is the mass of the cylinder in water? So now, this is very similar to problems you're going to see when you do your homework on Mastering Chemistry, or problems at the end of the book. Let's kind of make a map out of what this is going to look like. So at the end, we want to know, what is the combined mass of the cylinder and the water? So in other words, if we would think about it in terms of symbol, we want to know what the mass of the water is plus the mass of the cylinder. And together, we'd like to know what this total amount is. This is what we want to know right here. Now, which of these do we already know? The cylinder. The mass of the cylinder is how much? 100.57 grams. We already know that one. And so again, we're trying to find this here, the total. Now, we don't know the mass of the water yet, but what do we know about the water? What do we know about the water?
The amount of it?
Yeah, what do we mean when we say the amount?
Volume.
We know its volume, exactly. So we know that the volume of the water is 55.3 milliliters. Now we know the volume of the water. We should also know the density of the water. We already said that the density of the water is about 1. We should probably be a little more specific about it though. The temperature here today in this room, I have my thermometer out here right now. The temperature is 24.7 degrees Celsius. Now, because I know all sorts of trivia that I'm not supposed to really know, but I do, I happen to know that the density of water at this temperature is 0.997 grams per milliliter at a temperature of 25 degrees Celsius. Okay. Now, density is something that changes with temperature. That's why I specified the temperature. It's just the way hot air balloons work. A hot air balloon works because you heat up the air in that space above the basket, and that makes it less dense. And when you make it less dense, that causes the hot air balloon to rise. So, very often we give the density. If you look at that table here in your text, it probably says, and it doesn't say that, it should say it, these would be the densities probably at 20 degrees Celsius. So very often when we give the density, we should also specify the temperature at which it's measured. So now if we know the density and we know the volume, we can use the density and the volume to calculate the mass. Because of course, density is equal to mass over volume. So now the way that I think it's best to do this is to rearrange the equation first before you plug in any numbers. We have D is equal to m over v. We want to solve this equation for m, which is the mass. How do we get mass by itself? Multiply both sides by the volume, exactly. We multiply both sides by the volume. V here cancels out. And we find that the mass is equal to volume times density. So now if we plug these in, we have the volume, which is the 55.3 milliliters. We have the density, which is 0.997 grams per milliliter. We can then multiply these together. When we do, what happens to the units? Milliliters here should cancel out. Once they cancel out, we take the 55.3, we multiply that by 0.997, And we wind up with an answer of 55.13 blah blah blah. How many significant figures should this answer have? 3. So we'd round this off to read 55.1. Now if you wanted to carry along some extra digits, you could. Just remember that this digit here is the uncertain digit. And of course, whenever we write an answer here, it should also be accompanied by a unit. Units in this case would be what? Grams. So we come back here and put in the 55.1 grams, which is the mass of the water. So again, we put this up here. We can now sum these together. Once we sum them together, we get 155.67. However, we should round this particular answer off to being 1. How do the rules work with addition and subtraction?
Fewest number of decimal places.
Fewer number of decimal places. So this would be rounded off to 155.7. 155.7. So when you have mixed operations, multiplication, division, you always follow the order of operations. That is, you do all your multiplication and division first, which follows significant figures, followed by all of your addition and subtraction last, which uses decimal places. We wind up with 155.7. So then if we come back to our graduated cylinder and place this onto the balance, we should find a value of 155.7. And which digit, if there is a variation, which digit should we expect to see variation? All right, we should expect to see some variation in the last place. Of course, it depends upon how, oh my gosh, that's better than I ever done. Okay, that's just lucky. All right, we wind up with 155.7. It was supposed to come up with like 155.8 or 155, so we could talk about uncertain digits. Okay, but this is like a 1 in 10 year type thing here for me. So, any questions? And that's even without my glasses on. I'm pretty darn impressed. Okay, any questions? All right. Good job, Lance. All right. Now, next up, if we were to have a problem which we want to calculate the volume, let's go back to our formula. D is equal to M over V. We have D is equal to M over V, and we want to find out what V is. We want to get V by itself. How do we get V by itself? Yeah, now if we multiply by M, that's not going to work because both M and M are in the numerator. See, we can't do that because V sits down here in the denominator. So the first thing we have to do is get V up in the numerator, which means we have to multiply each side by V. Once we multiply each side by V, V cancels out. And we find out that V times D is equal to M, which is what we already said it is. And now to get V by itself, what do we do to each side? Divide by D. Whatever we do to one side, we must also do to the other side. So we cancel out the D. We find out if we had to calculate the volume, volume would be found by taking mass divided by density would be the way that this would be calculated. Now I sent some algebra phobia, okay, in here, and that's all right. So I'd like to use things called mnemonics. Anybody know what mnemonics are? This kind of has a funny spelling. Mnemonics. Anybody know what mnemonics are?
They're like word series that help you to remember.
Word series? They could be, yeah. That's one example of a larger scale. Like, for example, the first mnemonic I ever remember learning that was a word series was every good boy does fine. How many learned that one? What is it?
Music scale.
Music scale. Not the scale, but the lines on the treble clef. And then there was face, F-A-C-E, which would be the spaces on the treble clef. I was a bass clef person myself, but that's how I learned the treble clef. Okay, now in chemistry, we're going to learn about the density pi. All right? Now the density pi gets divided up like this. We're just going to cut it into 3 pieces. And the top piece, which is the big piece, we give to me, which is M. So M stands for me. And then in the bottom, I'm going to put V and D. And so the way this works is, whichever one you want to calculate, you cover it up, and that tells you how to do it. So if we want to calculate density, we cover up D, and that tells us to take M over V. If you want to calculate V, cover it up, and you get M over D. If you want to calculate M, cover it up, and you have V times D. So density pi, the way you make it is you cut it into 3 pieces. You give yourself me, M, the biggest piece, and put yourself on top. All right? Any questions? All right. Next up, we're going to use that handout. So pull the handout out here. Anybody not pick one? Okay, the handout has 2 sides. If you look at the one side, you'll see it's dated today. You flip it over, you're going to see it's dated next Tuesday. All right? That means don't lose this. Bring this back on Tuesday. We're going to work on the front side today. Flip it over. We're going to work on the back side next class. I don't have enough copies here for the people that were absent, so don't lose your copy. We're going to start by looking at physical change and chemical change. So we say that a physical change is a change in which no new chemicals are formed. Whereas a chemical change is a change in which new chemicals are formed. And so your test, whether it's a chemical change or a physical change, is to ask yourself, do we have the same chemicals at the end that we started with? And if the answer to that question is yes, that the same at the end as they are at the beginning, then the type of change you're looking at is a physical change. And if your answer to that question is no, then you have an example of a chemical change. So we're going to start off by looking at this reaction. And it's the very first one that's on your list there. They're numbered. We're going to do 8 demos here today. And the first one we're going to do is to combine some calcium chloride and sodium carbonate. Calcium chloride and sodium carbonate. And I'm going to pour them into different beakers. We'll put the calcium chloride into one, and we'll put the sodium carbonate into the other. And I just spilled a little bit here, so I need to add this up a bit. Okay. Now when we mix these together, notice that we have 2 clear, colorless solutions. We'll go ahead and pour one into the other. Let's watch what happens when we do that. Okay, now, this thing right here, we see that it's turned cloudy. This is an example of what chemists call a precipitate. So in your description there, it says that solutions of calcium chloride and sodium carbonate are mixed, and then you can complete it by saying yielding a white precipitate. Yielding a white precipitate. Now I need to redo this one because I forgot what I was supposed to demo with this one. So let me demo it again. I gotta pour the calcium chloride into here. I was supposed to weigh it. Do before and after. Alright. So we're going to put it on the balance. We'll do a before weight. And I think I need to take out an extra weight on this one. I do. So we're going to do a before and after weight on this one. Actually, a before and after mass. Even I have bad vocabulary. And I like to bring the old-fashioned one out here when I try to demonstrate stuff conceptually. And it looks like we have a mass here of, we can write this down, 224.3 grams. So 223.4 grams. And because I had to grab a dirty one, it looks like there's already a little bit of junk in this one here. But we'll mix it together. Once again, we get the formation of that precipitate. And the word precipitate means literally to fall out. The word precipitate means literally to fall out. And that's the term, again, that chemists give to this. Now, where have we heard of precipitate or precipitation before?
Weather.
Weather. So like rain or snow or sleet. That's falling out of the sky. As this sits here for a while, one of the things you're going to begin to notice is that this is going to settle down to the bottom. It's going to fall out of the solution, and it's going to become clear on the top as it settles down to the bottom down here. Now I'm going to place these back onto the balance in just one moment. Before we do that, however, what do you think will have happened to the mass? Do you think it will have increased, decreased, or stayed the same? By the way, the precipitate is a solid. That's why it looks cloudy in here. You have solid particles that are now suspended in solution. That solid will begin settling out as this sits here. And as always, feel free to discuss with a neighbor. Let's get our answers locked in, please. Count down. 5, 4, 3, 2, 1. I think the best way to do it, rather than reveal up there, is to actually test it on here. And if you were to look to see what happens to the mass, you should see here now it's bouncing back and forth equal distances. Its mass has done what? Stayed the same. It should have stayed the same. C, here's the correct choice. Should have stayed the same. And if we answer the next question on this, solutions of calcium chloride and sodium carbonate are mixed, yielding a white precipitate. Is this an example of a chemical change? Go back to the definition if you're not sure. Or is it a physical change? Right up, straight up in the middle here. So if we get our answers locked in again, please, we'll count down. 5, 4, 3, 2, 1. This here is an example of a chemical change. We have new chemicals here that weren't here at the beginning. And there's actually two things that happened here that would tell us that it was a chemical change. And so if you want to write down a special section here, what is evidence for a chemical change? Precipitate is one of them, exactly. So if you mix it together, some clear solutions, and you form a precipitate, that's one indication that a chemical change has occurred. What's another one?
Color change.
Color change, exactly. Color. So if you ever observe something change color, we have a white substance here now that wasn't here before. So that is evidence of a chemical change. Now the other thing we observed here, and you're going to go like duh when we say it, but the other thing we observed here is going to be the law of conservation. You know where this is going? Law of conservation of matter. And the law of conservation of matter says matter can neither be nor created nor destroyed. Matter can neither be created nor destroyed as a result of a chemical change. Now what happens is it changes forms, but let's say we were to think about atoms like nuts and bolts. Okay? If I had a bag full of nuts and bolts and those nuts and bolts weren't connected to each other, they were just separate nuts and bolts, but they were all contained in the same bag. We took them all out of the bag, we connected the nuts and bolts together, put them back in the bag and weighed it. How would that weight at the end compare to the weight at the beginning? Should it have gone up, down, or stayed the same? Should have stayed the same. So this is the same thing. If we think of atoms like nuts and bolts, all we're doing is we're either taking atoms and putting them together, or we are taking them apart. But we didn't put any atoms into here, we didn't take any atoms out of here. All the atoms that were in here are the same mass as they were before. We should expect to see no change in the mass. Okay, let's look at the next one. The next one we're going to look at is one that you've probably done many times before. I'm going to take some baking soda and vinegar. How many done baking soda and vinegar before? Sure, you all have done that before. What happens when you mix them together? You get bubbles, sure, and very often it's called a volcano reaction because if you mix them together very rapidly, it'll bubble and foam over. Now I'm not going to do it rapidly, I'm going to do it a little bit slower. And we'll go ahead and see what we get when we place these onto the balance. Slide this out here. Oh, looks like I'll need to put this mass on again. Okay. And this one here is going to be 200 something around 212 point. Not quite enough. Looks to be about 212.7 grams, 212.7. So now what I'm going to do is I'm going to mix them together. I'm going to mix them together a little bit slower than you would in their volcano reaction. I got one big chunk there that I don't want to go in. Yes, it probably will. So now we see some of the fizzing occurring here. And then what I'm going to do is I'm going to place them back onto the balance, and we're going to measure their mass. So your first question is on the Socrative app, right here, baking soda and vinegar mixed to yield, and you can complete this sentence on your sheet as well. So again, number 2, if you were to complete that, baking soda and vinegar mixed to yield carbon dioxide gas. The mass measured on the balance will, and let's just take one more piece here, drop it in. So I haven't spilled anything. I'm going to come back here and place it onto the balance. When we get our answers locked in, we'll count down. 5, 4, 3, 2, 1. And once we do so, what's happened to the mass? Yeah, if we look at the pans now, notice that it's not even pushing down at all. That means that this side here is too light. That means it has lost mass. And so we'd say that the mass will have decreased. You say, well, wait a minute. We just said that mass is conserved. Yes, it is. Well, what happened? Why did the mass decrease?
The gas.
Where is the gas? It's in the air, exactly. Now, there is a way to demonstrate the conservation of mass with this. How can we demonstrate the conservation of mass? Yeah, put a bag in it, or put it in like a 2-liter bottle or something. Okay, it's going to build up with a lot of pressure, but certainly if you can contain it all without letting it escape into the air, you could show that mass is indeed conserved. The other thing this shows is that gases must have mass. We saw that there was some bubbling in here, but we weren't able to capture it, so gases are a form of matter because they do indeed have some mass. Okay, next question. Baking soda and vinegar mixed to yield carbon dioxide gas. This is an example of. We'll get our answers locked in on this one, please. And we will count down. 5, 4, 3, 2, 1. This one here is indeed an example of a chemical change. So another piece of evidence of a chemical change, if you're making a list, is that when you mix chemicals together and a gas is produced, that is evidence for a chemical change having taken place. Okay, next on your list, we are heating sugar. So I'm going to put this up on the dot cam here, so you can see what's happening with this one. Oh, we need to put some sugar into it. How about we do that? I'll come over here and put some sugar in. There we go. That should be enough. And we'll go ahead and put this underneath the dot cam. Right there. So now here we are heating sugar until it melts. Not only is it melting, but what else is happening?
Is it burning?
You're seeing that it's turning brown. So now, I'm heating sugar until it turns brown. This is an example of what type of change? Oh, on your app. On your app there. We'll get our answers locked in on this one, please. We'll count down. 5, 4, 3, 2, 1. This, of course, is an example of a chemical change. What is our number one piece of evidence? Color change, exactly. We already said if we see a color change, that means that a chemical change has taken place. The other thing is, if you were to smell this, you think it smells the same as it did before? No. It's a change in smell. If you were to taste it, would it taste the same? I highly doubt it. Okay? So why we toast marshmallows, right? If you're up here close enough, you smell it. It smells like toasted marshmallows. Okay? Nobody likes plain marshmallows. You want them toasted, right? Okay, next one. We are going to heat sugar. Not sugar. This is water. Watch what happens to this one. We're heating water until it begins to boil. Heating water until it begins to boil. This will show up on your Socrative app next. Boiling water. Is this an example of a chemical change, or is it a physical change? Boiling water, is it a chemical change or a physical change? And we'll count down on this one. 5, 4, 3, 2, 1. It is indeed a physical change. When we heat the water up, we start with water and we end with water. We start with water and we end with water. In fact, if you looked at this test tube, it's kind of hot, but if you look up at the top of it, you'll see water condensing there. That's because the water turned from a liquid into gas. Once it got up to the cooler portion of the test tube up at the top, it recondensed back into a liquid. Next one here, I'm going to take some sugar. And if you're wondering why the water looks like this, it's just because there's air in the water. It's not because the water's dirty or anything, but the water's aerated. So now I'm taking some sugar and dissolving the sugar in water. Dissolving the sugar in water. It's like the sugar has pretty much now disappeared. But dissolved sugar in water, is this an example of a chemical change or a physical change? Get our answers locked in there, please. We'll count down. 5, 4, 3, 2, 1. We dissolve sugar in water. That is an example of a physical change. Example of a physical change. Because we started with sugar and water, and at the end we have sugar and water. Okay, doesn't change anything in the taste. You might look at the different appearance, but if we wanted to get the sugar back, what would be a very easy way to do it? Boil the water away or evaporate it away, and if we evaporate it away, we should see the sugar in there at the end. Now the next one, number 6 on your list. I have some natural gas. I'm burning the natural gas right here. Is this an example of a chemical change or a physical change? I am burning natural gas. So ask yourself, do we have the same chemicals at the end that we start with? Get our answers locked in, please. We'll count down. 5, 4, 3, 2, 1. It's 50-50, but the correct choice, in case you're red-green colorblind, is choice A here. This is indeed a chemical change. This is a chemical change. Whenever something is burning, now burning is not the same as heating. Burning is when you see a flame. When you physically see things burning, burning is an example of a chemical change. So if you're putting down evidence for a chemical change, burning something is an example of a chemical change. Next up, I have some magnesium. This one is to be done in the dark. Now when you look at this one, do not look at it directly. But it's a piece of metal, and I was going to put this under the dot cam. Here we go. Put under the dot cam right here. Go ahead and put it in the. We see now when this thing burns. There we go. Okay, and so now if I drop it back down in there and show you at the end what we have. At the end we have this white powder that's in there that was not in here at the very beginning. We started first of all with this metal right here, but in the end we wound up with this white powder that's present. So is burning magnesium example of a chemical change, or is it a physical change? Is burning magnesium an example of a chemical change or physical change? And then we'll get down to the last one. Come on. We'll get our answers locked in on this one, please. And we'll count down. 5, 4, 3, 2, 1. Correct answer here is that it is a chemical change. There's actually two pieces of evidence. What's one piece of evidence? It's burning. What was the other piece? Color change. There's actually two pieces of evidence that that was a chemical change. It was the fact that it burned, and then the fact that we saw the color change. Now the last one. I'm going to do some temperature measurements here. I've put in a solution of hydrochloric acid, and the other solution here is some sodium hydroxide. I'm going to go ahead and measure the temperature of these. We'll start first of all with the sodium hydroxide. Right here, we drop it in. We follow the temperature over here. Looks like we are at about 24.4 degrees Celsius. We'll dry this off. We'll put it into the hydrochloric acid. It looks like this one is sitting at a temperature of 24.2 degrees Celsius. So what I'm going to do is I'm going to go ahead and start recording the temperature. Remember that the two temperatures are about the same as 24.4 and 24.2. If I pour one into the other now, watch what happens here. At the same time we watch the temperature. Now of course when we mix them together, you might have seen that there's like a little bit of steam there, but really inside of here it doesn't look like a whole lot interesting has happened. But what's happened to the temperature? It went up. So in this case here, if you want to fill in the blanks, solutions of sodium hydroxide and hydrochloric acid are mixed, causing the temperature to increase. This would be an example of, fill in the blank. And if we count down on this one, 5, 4, 3, 2, 1. Correct answer is that this is a chemical change. So now, as you're writing down evidence for a chemical change, here's one more piece of evidence. A chemical change has occurred if there is a change in temperature. It doesn't have to be an increase like this. It can either be an increase or a decrease. But if we mix chemicals together, we see a change in temperature that tells us that a chemical change is taking place. That's it for today. See you in class next Tuesday. 2 assignments due before we meet again.